Hello AP Physics C Electricity and Magnetism students. Welcome to our video, our second lab video where I'm going to be performing an experiment for you and then you're going to be analyzing the data. At this point you should have printed out the lab sheets. Now you don't have to print out the first 2 pages, the instructions, because I already have those, and if you need to look at them, it's fine to look at them on your screen. Unless you want to print them out, make it easier to look at later. But what hopefully you are able to do is print out the lab analysis sheets. I should have mentioned this in the balloon lab as well. If you don't have a printer at home, this becomes pretty tedious. You're going to have to try and draw a replica of this using a ruler and pencil, and then submit that through photographs when you're done analyzing your data. That would be very tedious, so hopefully you're able to print. Okay, so let's get into the lab. Just want to say, maybe you're lucky you're not doing this lab in class, because this is a very tedious lab. So I'll have to do all the tedious part, and then you're just going to get the data. The purpose of this lab is to accurately map the equipotential and electric field lines in the space around 2 round conductors. The materials: power supply, multimeter. Okay, why is it called a multimeter? Well, first of all, it's a meter for electricity, and it does multiple things. Right now it's a voltmeter, measuring volts. Now it's an ohm meter, measuring ohms or resistance. We'll learn about what that means later in the year. And now it's measuring amps or current in a circuit. So it's multiple things, multimeter. Okay, but we're going to use it as a voltmeter in this lab. And then 3 alligator clip banana wires. So this, okay, it's kind of obvious why that's called an alligator clip. It looks like a little alligator mouth, but I'm not exactly sure why this is called a banana wire. Maybe it looks like a banana, but that's what it's called, banana wire. So we need 3 of those. Now I have, oops. Oh, looks like I grabbed the wrong wire. Hold on, I'll be right back. Okay, so I have 3 of these alligator banana wires, and notice that 2 of them are red and 1 is black. The color doesn't matter. They're all copper wire on the inside, so they work exactly the same. The color is just the plastic on the outside, the insulation part. The reason why wires are different colors are for humans to be able to see what wire is what. When you have them all coiled up like this, it gets confusing which wire starts and ends where. But when they're all color coordinated, that becomes easy. Okay? So the color is insignificant in terms of the function of the wire. And then we have another wire with banana plugs on both sides, banana, banana. And then a wood board with paper. Okay, so, and then 2 different colored markers. Well, obviously you're going to have find those at home. But this is the wood board. You notice it has a centimeter axis here, centimeter axis here. It's got grid marks. And then this is special ink that's conductive. So it has metal in this ink. And I've drawn 2 circles here, and there are 2 little bolts here that we could clip on so we could charge these conductors on this piece of paper. Okay, so that's what we're going to do. Okay, so now what I'm going to do is I'm going to move the camera and hopefully give you a view, an overhead view of what I'm going to be doing in this lab. Okay, so I won't read the instructions because I'm just going to perform them. So since you don't have to do them, I'll just hook this up. 1 wire goes like this to the power supply, 1 terminal of the power supply. We're going to learn throughout the year that one terminal of the power supply, one is always positive, the other one's negative. So then we hook that onto the left clip here according to the procedure. Then we go from the other terminal of the power supply to the right conductor. Okay. And then the right conductor, we will hook another alligator wire onto this right-hand conductor. I could just clip on like that, or inside the alligator clip, or try and get on the bolt again, but basically that works. And that wire is going to go to the COM port of the voltmeter. And the other wire, the banana wire, goes into this temp ohm volt. Again, this would all be in the procedure which I'm doing for you. This we will turn to 200 volts. And now I'm going to plug in my power supply into an outlet. Hopefully it works. I see a light on, that's good. And then I want to get up to 8 volts coming out of this power supply. And this adjusts like this so I could get whatever voltage I want here. But what I'm going to do is I'm going to put this on here, or I could actually put it over here if I want. But I'm going to charge this or increase the voltage on the power supply until the meter reads 8 volts. Uh-oh. So, problem. Oh. Could be a bad meter, so let me switch the meter out. Okay. There we go. So 8 volts. There we go. So there's... That's such a... It could be the wire. Let's see. Okay, that may have done the trick, hopefully. Okay, so I have 8 volts between these two conductors. So that's voltage as we learned in class. So what I'm going to do now is I'm going to take this probe, and by the way, all this we've done calling the teacher over. You don't have to do that obviously because I'm doing the procedure for you. So now I'm going to use the probe, the banana wire, and find a point on the paper that's pretty close to 1 volt. Using the grid on the black sheet and the grid on your answer sheet, mark your answer sheet with a point at the location of the 1 volt reading. So 1 volt, let's try right here. 8 volts, no good. 0 volts, no good. We're looking for 1 volt. Let's try in the middle, 4 volts. So obviously we want to be closer to this conductor. We'll move around until we find about 1 volt. And as I would say in class, it doesn't have to be exact. If it's 0.9, close enough. But we're looking at maybe 0.4 of a grid mark away from this conductor. Or we could use our axes, 16.6 and 10. And then we go to our grid here. And we go 16.4. 16 is right here. 16.6 is right about there, and 10. So I'll just put a light number 1 there, okay? Now, the procedure says 3, find 7 other points of approximately 1 volt. Mark their locations with points and labels on the white sheet. Your 8 points should span as much of the paper as possible. To speed the process, you may use symmetry to find points. For example, if there's 1 point at 12:14, right? There will likely be one at 12:06, right here. symmetry, right? So one above, one below, same x coordinate. So what does all that mean? So we had a 1 volt point right here. So we look for another 1 volt. Obviously, we're not going to go this way or that way. What we can do is go somewhere maybe like right here. That's 1.8. So I got to move it back to the 0. 1.1. 1.0. Looks like I am at the coordinate, what's that? 16.9 and 8.2. 16.9 and 8.2. 16.9 is right there, and 8.2 is right around there. So right there, we've got another 1 volt point. Okay? So since I had one here, there is probably one right here. And pretty close, I see one. Yeah, there we go. So there is one symmetrically above, the same distance above. So here is the same x coordinate. We go up to right around there is another 1 volt point. Now, maybe somewhere around here, 1.3. I got to get closer to this one, which is 0. Somewhere around, let's say, right there. So we're at 19 and 6.3. 19 and 6.3. So here's 19 and 6.3 is right around here. So there's another 1 volt, and there probably is one up here as well, okay, above the axis. So let's see if we can find such a point. Yeah, right around there. A little asymmetric, that's okay. So at 19, we go up to about 13 and a half. So 19, 13 and a half, right there, another 1 volt. So I'm up to 5 points. I need 3 more. So let's try and go somewhere back here. 0.8, let's go a little further away. 1. So looks like we are at 12 in the y coordinate and a little less than 26 in the x coordinate. So 12 and a little less than 26. So 26. So right around there is another 1 volt. There'll probably be one right there as well. So let's check and see if that's correct. So 26, okay, right. So we are at exactly 8 and 26. So 8 and 26, right there, another 1 volt. And let's see if we could find one on the axis here that's 1. All right, yeah, right on the mid-axis at 27. So we get another 1 volt. Okay, that is 8 points now that we have that are all equipotential, all equal volts, all 1 volt compared to this conductor. So we just completed step 3. Step 4, before proceeding, connect all 1 volt points using a pencil and a smooth curve. Once you are satisfied with your curve, retrace it with a colored marker A. The reason why we don't use the marker right away, what happens if you make a mistake? You start over, right? So we want to sketch with a pencil, something like this. Well, I'm satisfied with that curve, so I would just go back with a marker. I don't have markers with me. They're in the front of the room, so rather than create a delay, we'll just move on and we'll fill that in later with a marker. But we've connected the points. Okay, so now we're on to step 5. Repeat steps 2 through 4 for 2 volts, 3 volts, 4 volts, up to 7 volts. So we have 7 more voltages to go, okay? And 8 points, we got to find 56 more points, okay? So as I said, tedious and long, but I won't make you watch the whole thing in video because that's just, kind of pointless. But what I'm now looking for is 2 volts. So 1 volt was somewhere around here, right? So 2 volts, well, this is 8, so I want to move to the left till I find 2 volts. A little too far. Right about there at the midpoint, about 1.1 spaces away from that conductor, I will have a 2 volt line. So right there is a 2 volt point. Okay? By the way, I marked these with 1, but you shouldn't have. I'll erase those later when I post this online. But basically, that shouldn't be marked because later you're going to mark it with a different set of voltages. But I put a dot for the 2 volt, and I'm going to look for 7 more. So maybe one right here. Okay, so yes, maybe I'll go a little further. All right, so right there, I will mark that at 7.3 and 16.3. 7.3, 16.3. Right there is a 2 volt. And then I will go above the same location approximately, and doesn't have to be perfect. So there we go, close enough. I'm at 16.5 and 13. 16.5 and 13 is right there. Okay. That doesn't look very symmetric. 16.5. Oh. No, 12.5 and 16.5. Okay, so 12.5 and 16.5. Oh, I was off both. Okay, there we go. All right, so I'm going to pause the video here, and I'll find the other points, okay? Okay, so I found actually, I think 9 points. But again, I'm going to connect this with a smooth curve. Something like that. Now, it ultimately would wrap around, but the paper that I have is not large enough, so it's not wrapped around, okay, on this diagram. All right, now what I'm going to do is I am going to find 3 volts. So 2 volts was somewhere here. So 3 volts will be a little bit more this way, right here at 15, oops, a little too far. Well, close enough, right around 15 and the midpoint axis. So I'll put a mark right there. There's the 3 volts. Next, what I'm going to do is I am going to, find 7 more points. So if this was 3 volts, then maybe I'll find another 3 volts somewhere around here. Yes, I do. I mark that point right there on the white paper, and maybe the same distance above. Again, there's a symmetry here. So yes, somewhere around, right around there. Oops. Right around there. It doesn't have to be exact. So I'm going to pause the video and go ahead and find all those other points and show them to you in a minute. So I found those points. I think what I'm going to do when I give you these points, I'll probably try and have some kind of legend and have like triangles and squares and X's and O's. So, because you're supposed to connect these, but if I don't connect them, it would be very confusing if you just see all those points. So that's what I'm going to do just for your information. When I give you these points, they will be in that form. Now, so I found what are the 3 volt on the multimeter. Next, I need to find the 4 volts, and that is going to be, should be right in the middle between the two conductors, and it is. So right around, I put 1 point at the origin, and then I could maybe try up here. Looks like a little bit this way, but basically the 4 volt should be pretty close along to this central axis for all the points involved. You see 4, 4, roughly 4, maybe a little bit this way, so right, but pretty much along this. I'll go ahead and map it carefully, but that's what you would see. The 4 volt lines are right pretty much down the center. Okay, so I'll pause the video and show you the results. Well, hopefully you could see these points are pretty close to that center line. This is, if I put my meter here, 0 volts, the meter registers 8 volts on the conductor here, so obviously that should be right in the middle, the 4 volts. I'm next going to find 5 volts. So I went up to 4. Obviously I'm going to go this direction, continue in this direction for 5 volts. A little too far, so maybe I'll go right around there. Okay, so 5 volts right around there. And then I'm going to go above here and look for 5. So now this way, okay. Symmetrically over here, I should have another 5 volt, something like that. So I'm going to go ahead and map those points now. So I found more than 8 points here, but you can see there's a general pattern like this. Okay, so it's starting. The 4 volt went straight up and down. This one's now starting to curve this way. The others will curve that way. So that's the pattern we're going to see. The next one, 6 volts. So 5 volts was here. We're going to look for 6. Looks like right around here, right there is a 6 volt. Oops, 6 volt. And then I'm going to try something maybe like over here, a little bit more. Okay, so somewhere here. And then symmetrically down around here, I'm going to try for a 6 volt. Looks good. So now I'm going to map 8 points like that. So I'll pause the video. Okay, so I found a bunch of points here. Again, you would take a marker or pencil first and make a smooth curve like this, and then retrace that with a marker. So that was 6. And we have one more, the 7 volt line, 8 more points. So 6 was somewhere here, 7 might be right around there. Looks like there is about a 7 volt right around here, just a little bit away from that conductor, and then we look for maybe another 7 volt over here. Okay, there's one. There should be a similar point right here, so we go down here, and looks like somewhere around there. And then we're going to go ahead and I'll map out the rest of those points and show you the results in a minute. Okay, found another 8 points. So here they are. Again, you're going to take these and sketch in with a pencil. This isn't a very good job, a little too sharp here. Should be maybe try and get it a little more rounded here or something like that. But there they are. Now, you see the pattern, if you can see it, is not perfectly symmetrical, and that's okay. It's because the paper might not be consistent thickness throughout when it was manufactured. Maybe the ink wasn't laid down when I drew those circles perfectly, but it works for our purposes. So what I'm going to do is I'm going to post this, but with each of these points with some kind of legend, like maybe circles and triangles and X's and O's, and or letters or something like that. And then you're going to connect the dots in the proper fashion like I did. Trace them over nicely with markers, sketch electric field lines with pencils, put the electric field lines in properly. So remember, electric field lines have to start at one of these conductors and end up at the other. Maybe it starts at this one, goes to that one, but you have to make them cross 90 degree to each of the equipotential lines and begin and end at the right conductors. And then once you get those to your satisfaction, you trace the electric field lines in a different color marker. And you color in the legend here, which are the electric field lines and which are the equipotentials. So 2 markers. All of these voltage lines are the same color, maybe red, 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 for each of the voltage lines, the same color. And then you color this red because that's the equipotentials. Then maybe you do blue lines for the electric field lines. And maybe they go like this. You draw in all these arrows in the right shape. Practice, do it, get it just right. I'll be marking off for every little inconsistent thing. And then the blue lines are electric field lines, so I'm going to color that in blue. And that is the mapping lab, the data. What you're also going to do is obviously answer all these questions, okay? And then answer these questions on page 2. And then step 9, you're basically drawing this over, but in an idealized form. Like, for example, these two equipotentials are not symmetric. They should be in a real lab. If this were, perfect, theoretically, these should be the same shape. So you're redrawing everything according to how it perfectly should be, with the legend here and the 2 different color markers for the equipotentials and the electric field lines. Once you are done with all of this, as in the balloon lab, you're going to take photos of these 2 pages, zoom right in so I can see, submit those for your lab, and that'll be it for the lab. Just the photos, and I'll look at them and grade them. So that is the electric field mapping lab. And I'll see you in the next lab video. Okay.